Limits at infinity, horizontal asymptotes. In this section, we are going to learn how limits at infinity are used to find horizontal asymptotes. Limits at infinity. Limit of 1 over x as x approaches to infinity is equal to 1 over infinity, and when numerator is fixed as a number and when denominator gets bigger and bigger and bigger, then the whole quotient will go to 0. And that is true even if the number in the denominator goes to negative infinity. So limit of 1 over x as x approaches to negative infinity will be equal to 1 over negative infinity, and this still goes to 0. In fact, if c is any constant real number and n is any positive number, then limit of c over x to the nth power as x approaches to infinity is equal to 0. So it doesn't matter what kind of constant it is, as far as your numerator is fixed and denominator is getting bigger and bigger, and that will always result in limit of 0. So now look at this example. Limit x approaches to infinity of 4 billion over x squared. Well, now my constant c is so huge. Doesn't matter. 4 billion is still nothing compared to infinity in the denominator. Not only that, you have infinity square. So this will be equal to 4 billion over infinity square, and it will still go to 0. So here is now definition of horizontal asymptotes. The line y equal L is a horizontal asymptote of f of x if either limit of your function as x approaches to infinity gives you a real number L, or limit of your function as x approaches to negative infinity gives you L. You have a horizontal asymptote y equal L. And they don't have to be matched. You could have a limit of a function value as x approaches to infinity could be L. Limit of f of x as x approaches to negative infinity could be k. So you could have 2 horizontal asymptotes. As you can see, since this is the definition of horizontal asymptotes, you could only have at most 2 horizontal asymptotes, since horizontal asymptotes comes from this definition of limit. And you can only send x to either infinity or x to negative infinity. And sometimes they could be the same number, so that you would only have 1 horizontal asymptote, and sometimes the limit would not reach to any real number, therefore you might not have any horizontal asymptotes. So now look at the example below. Use the limit to describe the behavior of f of x at the horizontal asymptotes. So let's see, first of all, what is the limit of your function f of x as x approaches to positive infinity. So as x approaches to positive infinity, your function value is reaching. It is keep reaching to the value here, which is negative 3. So this limit is negative 3. Your function is reaching to negative 3 as x approaches to positive infinity. So by the definition above, you do have a horizontal asymptote, which is y equal negative 3. How about limit of this function as x approaches to negative infinity? As x approaches to negative infinity, you can see your function is trying to reach to where? This value, positive 3. So the limit is positive 3. Therefore, you have another horizontal asymptote, which is y equal 3. Evaluate the limit. I have a limit of negative 8 plus 5 over x as x approaches to infinity. So we have learned in the past that limit of the sum is sum of the limits. So I could split this limit and have a limit of negative 8 as x approaches to infinity plus limit of 5 over x as x approaches to infinity. And as you know, limit of a constant is a constant. So this limit will go to negative 8, and limit of 5 over x as x approaches to infinity is what we learned today. When we are taking limit of a quotient where numerator is a fixed constant and denominator goes to infinity or negative infinity, we know the resulting limit is 0. So therefore, the limit is negative 8. Although that's not what this problem asked. Just for your information, this function, negative 8 plus 5 over x, will have a horizontal asymptote y equal negative 8. Next example, evaluate the limit. I have a limit as x approaches to negative infinity of 2 plus sine x over x squared. So again, we're going to split this and do limit of 2 as x approaches to negative infinity plus limit of sine x over x squared as x approaches to negative infinity. And we already know limit of 2 as x approaches negative infinity is 2. And what is the limit of sine x over x squared as x approaches to negative infinity? I know denominator is going to get huge, but sine of negative infinity, I don't know what that value is, right? So we're not so sure what this limit value would be. So in this case, we need to use special technique we learned in the past. As you know, sine function, its range is from negative 1 to 1. And since x is going to negative infinity, x is not 0. So when you square the x squared will be for sure positive. So we can divide all three sides by x squared, and because it's a positive value, it will not change the inequality. And now you could use squeeze theorem. Limit of negative 1 over x squared as x approaches to negative infinity has to be then less than or equal to limit of sine x over x squared as x approaches to negative infinity, and that has to be less than or equal to limit of 1 over x squared as x approaches to negative infinity. However, limit of negative 1 over x squared as x approaches to negative infinity, as we learned today, it is 0, less than or equal to limit sine x over x squared as x approaches to negative infinity has to be less than or equal to, and limit of 1 over x squared as x approaches to negative infinity is also 0, as we learned today. So by squeeze theorem, limit of sine x over x squared as x approaches to negative infinity is 0. So as we kind of thought what the limit would be, it turned out to be true. So this is going to be 0, and the limit is 2. So again, they didn't ask. When they just say evaluate the limit, all you have to do is evaluate the limit. But just for your information, that means this function has horizontal asymptote y equal 2. Compute each limit to determine if the function has a horizontal asymptote or not. I have a limit, quantity 9x plus 7 over quantity 3x minus 6 as x approaches to infinity. If I were to substitute infinity for x, I'm gonna get infinity over infinity, which is undefined. So substituting infinity for x isn't gonna work in this case. So when you get a case like this, technique for solving limits like this is to multiply by a quantity 1 that will make a quotient of constant over variable so that we know that limit of that would be 0. What I mean by that is if I were to multiply quantity 1, that is 1 over x over 1 over x, and now when you distribute it, x will cancel and you're gonna get just 9. And then when you multiply with 7 times 1 over x, you're gonna get 7 over x. And you know limit x approaches to infinity of 7 over x, as we learned today, it is 0. So that's good. And when you distribute 1 over x times 3x, x cancel and you're gonna get 3. And when you distribute again 1 over x with negative 6, you're gonna get negative 6 over x. And you can set the limit as x approaches to infinity to each of the term, which will result in limit of 9 is 9, limit of 7 over x as x approaches to infinity is 0, limit of 3 is 3, and limit of negative 6 over x as x approaches to infinity is 0. So you're gonna get 9 over 3, which is 3. And since limit of this function as x approaches to infinity is 3, which is a real number, you know this function has horizontal asymptote, which is y equal 3. Next question. How about limit quantity 3x squared plus 2 over quantity 6x squared minus 5 as x approaches to infinity? Again, if you were to do the direct substitution of infinity for x, you're gonna get again infinity over infinity. So in this case, we're gonna multiply by quantity 1 that would give me a rational expression of constant over the variable. And this time, since our variables are x squares, you want to multiply by 1 over x squared on the top and 1 over x squared in the bottom. So that would give me, as you distribute first, x squares get canceled. So you are gonna get limit x approaches to infinity of numerator, my first term becomes 3. And when you multiply by second term, 2 times 1 over x squared is plus 2 over x squared. When you distribute with denominator, the first term 6x squared times 1 over x squared is gonna get canceled. So you get 6 minus 5 times 1 over x squared, which is 5 over x squared. So then you will have limit of 3 is 3. Limit of 2 over x squared as x approaches to infinity is 0. Limit of 6 is 6. And limit of negative 5 over x squared as x approaches to infinity is 0. So I get 3 over 6, which is 1/2. So this function also have a horizontal asymptote, and it is y equal 1/2. How about next example? I have a limit of quantity 3x plus 2 over quantity 6x squared minus 5 as x approaches to infinity. Now, this time, the degree of numerator is not equal to the degree of the denominator. So what do we do here? So the tip is always use the biggest exponent up here in the denominator. So as my numerator has a degree 1 and denominator has a degree 2, we're going to use biggest exponent up here in the denominator, which is degree 2. So again, we're going to multiply by quantity 1 over x squared over 1 over x squared. So then that will give me limit x approaches to infinity of. Now when you multiply with this one, x cancel, so you get 3 over x. And when you multiply with second term, 2 times 1 over x squared gives you 2 over x squared. And when you distribute the first term of the denominator, you get x squared cancel, so you get 6. And when you multiply by second term of the denominator, negative 5 times 1 over x squared will give you negative 5 over x squared. And then if you take the limit of each, limit of 3 over x as x approaches to infinity is 0 plus limit 2 over x squared as x approaches to infinity is 0. Limit of 6 is 6. Limit of 5 over x squared as x approaches to infinity is 0. So you are going to get 0 over 6, which is 0. And 0 is a real number. So you do have a horizontal asymptote, and horizontal line will be y equals 0. What is y equals 0, guys? Yes, it is x-axis. So this rational function will have horizontal asymptote, which is x-axis. Last question. Limit of quantity 3x squared plus 2 over quantity 6x minus 5 as x approaches to infinity. This time, I have higher power in the numerator. However, our tip was to use the biggest exponent up here in the denominator. So you are going to still multiply in the form of 1 over x over 1 over x, because in the denominator, highest power is x to the first power. Why not x to the second power on the numerator? Why don't we use that? Because if you were to do that, if you remember what happened to the third example we just did, we're going to end up getting 0 and 0 in the denominator, which will just make it undefined. So we don't want that to happen. So we're going to use the biggest exponent up here in the denominator. Don't forget that. So then limit x approaches to infinity of, as we distribute the first time on the numerator factor, 3x squared times 1 over x. Only one factors of x cancel from 3x squared. You will still have 3x as the first term. When you multiply with 2 times 1 over x, you get plus 2 over x. As you distribute to the first term in the denominator with 1 over x, you get x cancel, you get constant 6, minus 5 times 1 over x will give you 5 over x. So as you send the x to infinity, 3x will go to infinity, plus 2 over x will go to 0. Limit of 6 is 6, minus limit of 5 over x as x approaches to infinity is 0. So I get infinity over 6, meaning my numerator is going to keep getting bigger and my denominator stays as a 6. And result is, of course, infinity. And because my limit is not a real number and it is infinity, that means you're not going to get a horizontal asymptote here. Use the previous example to summarize when a rational function will have horizontal asymptote. So if you look at the first two examples, my numerator and denominator have the same degrees. First one, degree of numerator is 1, degree of denominator is 1, and I do have a horizontal asymptote. In the second example, degree of numerator is 2, degree of denominator is 2. I do have a horizontal asymptote. Third example, degree of numerator is smaller than the degree of the denominator, and I still had a horizontal asymptote. However, as degree of numerator is bigger than the degree of denominator, you can see every time that happens, I'm just gonna get a number in the bottom and infinity on the top. So I'm not gonna get a limit as a real number, which result in no horizontal asymptote. So you can conclude that horizontal asymptote only occurs when degree of numerator is less than or equal to the degree of denominator. So we can summarize that, and you can also remember it. In next example, you're gonna find the horizontal asymptote involving square root function. So recall from algebra class, square root of x squared is not x because we don't know whether x is positive number or negative number. X is a variable. Note that square root of x squared is absolute value of x, and if we know the x is a positive, then absolute value of x will be x. But if x is a negative number, then it's gonna come out as opposite of x. So for example, square root of negative 3 squared is not negative 3. If square root of x squared was just a x, square root of negative 3 squared should be negative 3. But no negative number can come out from square root. So this will come out as an absolute value of what's inside. So it gives you positive number 3. Example, compute each limit to determine if the function has a horizontal asymptote or not. I have a limit x approaches to infinity of quantity 12x minus 5 over square root of quantity 9x squared plus 1. If you were to substitute infinity for x, again, I'm gonna get infinity over infinity. So substituting infinity for x doesn't work here. So we're going to multiply by quantity 1 that uses the highest power of the denominator. And in denominator, since you have a square root of something, highest power is a square root of x squared. So we are going to multiply by 1 over square root of x squared over 1 over square root of x squared. But then square root of x squared is absolute value of x. But because x approaches to positive infinity, x is a positive number, so square root of x squared is an absolute value of x, and because x is positive, it is just x. So this is the same thing as limit x approaches to infinity, quantity 12x minus 5 over square root of quantity 9x squared plus 1 times 1 over x over, I'm gonna leave the bottom one as a square root of x squared. They're the same thing right now because you can see square root of x squared is equal to x. I changed that to 1 over x on the numerator since it has to be distributed with 12x minus 5. And in the bottom, I do have a square root already here, so it's easier to have a square root of x squared form, since square root of a times 1 over square root of b is square root of a over b. So now, this is equal to limit x approaches to infinity. Go ahead and distribute with this, X cancel, you get 12 there, minus 5 over x. And in the denominator, you can form square root of a times 1 over square root of b equal square root of a over b. So this will become square root of 9x squared plus 1 over x squared. So then you can split the numerators using common denominator x squared. This become limit x approaches to infinity of 12 minus 5 over x over square root of 9 plus 1 over x squared. So as x approaches to infinity of 12 is just 12 minus limit x approaches to infinity of 5 over x is 0. And as x approaches to infinity of square root of 9 plus 1 over x squared will go to square root of 9 plus 0, which is equal to 12 over square root of 9 is 3. So it is 4. So we do get horizontal asymptote here, and it is y equal 4. And you can see that because the square root of x squared is an x if x is positive, square root of x squared is opposite of x if x was a negative. So if x goes to negative infinity, then x is a negative number, so square root of x squared is equal to opposite of x, which will result in 2 horizontal asymptotes for this function. So this time, limit as x approaches to negative infinity, quantity 12x minus 5 over square root of quantity 9x squared plus 1. Same thing again, we're going to multiply by quantity 1, that is 1 over square root of x squared over 1 over square root of x squared, since we're going to use highest power in the denominator, and that is the square root of x squared. However, because x is approaching to negative infinity, x is right now a negative number, so square root of x squared, which is an absolute value of x, will come out as opposite of x. So this is really now 1 over minus x. And in the bottom, we're going to leave it as a 1 over square root of x squared. So the next step, limit x approaches to negative infinity. When you distribute negative 1 over x times 12x, x cancel. Don't forget the negative. I'm going to get negative 12 here. And negative 5 times negative 1 over x will become positive 5 over x. And inside of radical, I'm gonna get 9x squared over x squared is 9. And 1 over x squared become 1 over x squared again. So when you send the x to negative infinity, limit of negative 12 as x approaches to negative infinity is still negative 12. Limit as x approaches to negative infinity of 5 over x goes to 0. And inside of a square root, as x approaches to negative infinity, square root of 9 plus 1 over x squared will go to square root of 9 plus 0, which is equal to negative 12 over square root of 9 is 3, which is negative 4. So again, you do have another horizontal asymptote, which is equal to y equal negative 4. So if your rational function has a square root and the degree of numerator is less than or equal to the degree of the denominator, then expect to have 2 horizontal asymptotes. In this example, we're going to use everything we have learned so far to sketch a graph of a function. And this is what you're gonna do whole time in 3.6. Find any roots, intercepts, asymptotes, extrema, points of inflection, and sketch the graph of fx equal 6 over quantity x squared plus 3. So let's first find the roots. What's roots? Roots are x-intercepts. And how do you find the x-intercepts? You set y equals 0. And y is f of x. So we're gonna set 0 equal 6 over x squared plus 3. And any fraction is 0 when numerator is 0 and denominator is not 0. You notice that x squared plus 3 is always greater than or equal to 3. So it cannot be 0. So this quantity is never undefined and cannot be 0 since your numerator is set to be 6 all the time. Therefore, this function do not have any x-intercepts. So therefore, there is no roots. Secondly, it's asking you to get intercepts. And since there's no x-intercept, all you have to do is now find the y-intercept. And how do you find the y-intercept? Yes, set x equals 0. So you get y equal, since f of x is equal to y, 6 over 0 squared plus 3, which is 6 over 3. So it is 2. So when x is equal 0, y is equal 2. And this is your y-intercept. Thirdly, it's asking you to get asymptotes. And again, we said earlier, this denominator, since it's always greater than or equal to 3, it cannot be 0. And your vertical asymptotes occur when denominator is 0 and numerator is not 0. Therefore, you do not have a vertical asymptote. How about horizontal asymptote? Horizontal asymptote occurs when degree of numerator is less than or equal to the degree of denominator. And what is the degree of numerator? You don't have any variable. You have a constant 6 on the numerator. So degree is 0. What is the degree of denominator? Degree of denominator is 2. And because 0 is less than or equal to 2, it qualifies the condition of having horizontal asymptote, and you will have a horizontal asymptote. And how do you get horizontal asymptote? We check limit as x approaches to infinity of your function, 6 over x squared plus 3. And because I do not get infinity over infinity, you can go ahead and substitute infinity for x. And if you do, you will get 6 over infinity, which goes to 0. And if you send the limit x approaches to negative infinity of 6 over quantity x squared plus 3, you still get 6 over infinity since negative infinity square will be positive infinity. I still get 0. So you have one horizontal asymptote, y equals 0. Next, it's asking you to find the extrema and points of inflection, and then we're going to use all the information we gathered so far, and we're gonna sketch the graph on the right hand side. So now let's go ahead and find extrema. And we have learned that extrema occurs on critical points only. So let's first find the critical point. F prime of x equal, let me rewrite my function as 6 times x squared plus 3 to the negative 1 power, so it is easier to find the derivative. So I'm going to use, of course, power rule and chain rule to take the derivative of 6 times function raised to the negative 1 power. So then f prime of x is negative 6 times the function x squared plus 3, lose 1 power, so minus the second power times chain rule. take the derivative of inner function, which is 2x. When you simplify this, it is negative 12x on the numerator, and you have x squared plus 3 to the positive second power in the denominator. And critical numbers are numbers such that f prime is 0 or f prime is undefined. So when is f prime 0? It is 0 when numerator is 0. When is numerator 0 and denominator not 0? If x is 0, numerator is 0, and denominator is still 0 plus 3 quantity square, which is 9. I get 0 over 9. So 0 is my critical number. And when my f prime does not exist, well, look at your f prime. My denominator is always defined. No matter what x you plug it in, this is always defined. So my f prime always exists, and this never happens. So you only have a one critical number. So then my critical number is 0, and pick any test point before 0. I'll pick negative 1, and after 0, I'll pick a positive 1 for test point. So let's plug it into f prime. So what's f prime of negative 1? F prime of negative 1 is negative 12 times negative 1 over quantity negative 1 square plus 3 square, which is positive. So this whole quotient will become positive. And what's f prime of 1? F prime of 1 is negative 12 times positive 1 over quantity positive 1 square plus 3 square, which is positive. So this whole quotient becomes negative. That means your function is increasing and then decreasing. So you will have relative maximum, and your relative maximum occurs at 0, and it will be f of 0. So go back to original function to find the y value. And original function is f of x equals 6 over x squared plus 3. So your relative max is equal to 0, comma, and it is f of 0. F of 0 is 6 over 0 squared plus 3, which is a 6 over 3. So it is 2. Because I have to get points of inflection, I'm going to get the second derivative. So then f double prime of x is equal to, I'm actually going to rewrite f prime of x and use the product rule instead of quotient rule. So if you rewrite this, this is equal to negative 12x times quantity x squared plus 3 to the negative second power. So that will be negative 12 times x squared plus 3 to the negative second power plus negative 12x times derivative of quantity x squared plus 3 to the negative second power will be negative 2x squared plus 3 to the negative third power times the chain rule 2x. So then this is equal to negative 12 x squared plus 3 to the negative second power. And let's go ahead and multiply the negative 12x and negative 2 and positive 2x all together gives me positive 48x squared. And now I still have x squared plus 3 to the negative third power. I'm going to factor this now to simplify this. And they both have negative 12 as a common factor. And between quantity x squared plus 3 to the negative second power and quantity x squared plus 3 to the negative third power, which is the smaller power of the two? Yes, negative 3 is smaller than negative 2. So you're going to factor out x squared plus 3 to the negative third power, open bracket. So then what do you have to multiply with what you factored out so that you can have your fourth term back? That will be x squared plus 3 to the positive 1 power, since we add exponent of the same base when we multiply. And then negative times negative gives you positive. 12 times 4 is 48. You still got an x squared, and then whole quantity x squared plus 3 to the negative third power is out in the front. So that's it for the second term. But then you notice inside of a bracket, I have a x squared minus 4x squared, so we can simplify more. So this is equal to negative 12 x squared plus 3 to the negative third power, and you get negative 3x squared plus 3 is what you get, which you could also factor out negative 3 in the front. So if you factor out negative 3 in the front from the bracket, negative 3 times minus 12 give you positive 36, which will leave you x squared minus 1 inside of a bracket. X squared minus 1 factors as x plus 1 times x minus 1 over, I'm going to send the negative exponent to the denominator. So it is over quantity x squared plus 3 to the positive third power now. So this is your second derivative. So now to find the point of inflection, we first find the number such that f double prime is 0 or f double prime does not exist. And this becomes 0 when x equal plus or minus 1. Since the numerator is 0, then this whole quantity is 0. And denominator, we said it whole time, it can never be undefined. So does not exist, gonna never happen for this case. So these are two possible points of inflection. Now, to determine whether I do have a point of inflection or not, let's locate negative 1 where the negative 1 is above, and a positive 1 because these are the two numbers such that f double prime is 0. And you will have inflection points if there is sign change before and after these numbers. So pick a test point for f double prime. Any number less than negative 1, let me choose negative 3. And number between negative 1 and 1, of course I'll pick 0. Any number after 1, let me choose 3. I'm going to use a factored form of f double prime to determine the sign. Let's plug negative 3 to every x you see. So 36 is a positive, so it's not going to affect your sign at all. So you can plug it into x plus 1. Negative 3 plus 1 is negative. Negative 3 minus 1 is negative. In the bottom, negative 1, you're going to square it and then add 3. So that's a positive number. Positive number cube is positive. So this whole quantity will become positive. How about you plug 0 for every x you see in the f double prime? So f double prime of 0, 0 plus 1 is positive. 0 minus 1 is negative. 0 squared plus 3 is positive. Positive number cube is positive. So this whole quotient will become negative. So f double prime change the sign before and after the negative 1. So negative 1 is the x coordinates of the point of inflection. How about 1? Well, we gotta check the signs for 3. So if you plug 3 to f of double prime, it is 3 plus 1, positive, 3 minus 1, positive. In the bottom, 3 squared plus 3 is a positive. Positive number cube is a positive. So I do get positive. So again, there is a sign change before and after the 1. And so 1 is again the x coordinates of the point of inflection. So then you do have 2 points of inflection at -1 and at +1. And you can find those points by plugging these x values into original function. So 2 points of inflections are -1 comma f of -1 and 1 comma f of 1. Because our original function is 6 over quantity x squared plus 3, whether I plug x for +1 or -1, when you square it, we're gonna get the same y value. So I can just calculate 1 and use it for both of the y coordinates. So y is equal 6 over 1 squared plus 3, which is equal to 6 over 4, which is 3 over 2. So 2 points of inflections are -1 comma 3 over 2 and 1 comma 3 over 2. So let's use all this information to graph this function f of x equals 6 over quantity x squared plus 3. So I had no roots, meaning my graph will not touch the x-axis. I do have a y-intercept 0, 2, and that happened to be also my relative maximum here. I do have a horizontal asymptote, and it is y equals 0, which is the x-axis. So I will have a horizontal asymptote, which is x-axis. Next, points of inflection, we had 2 of them. -1 comma 3 over 2. 3 over 2 is 1.5. So -1 comma 1.5 is the inflection point. I have another one at 1 comma 1.5. From -infinity to -1, I had f double prime positive. So that's a concave up. Concave up was cup shape. And I have horizontal asymptote, and graph should be increasing. So it's increasing with having horizontal asymptote in mind. Your graph should be shaped like this. So it looks like a cup, but it is increasing from left to right. Now concavity changes to negative. So between points -1 to 1, concavity is negative. It's a concave down. And concave down was umbrella shape. And you can also see your graph is still positive from -1 to 0, meaning it is increasing, but it has to be now concave down. So you can change this to umbrella shape. Now 0 to infinity, graph is going down. So it's gonna go down, but concavity is still down up to 1. So it's still umbrella shape up to 1 here. But now concavity change again to from 1 to infinity. It's a concave up now. So it's gotta be again cup shape. So your graph will look like that. So you just tasted what's coming in 3.6. So be prepared and see you at 3.6.